going? I'm Zane from thecarbondoctor.com. So today we're continuing with our whiteboard lecture series, and we're going to discuss the topic of hybridization. So this is a common topic in the chemistry curriculum that you're going to need to sort of understand to sort of take it on to more complex topics in organic chemistry. Okay, and so to start with, we sort of have to understand where hybridization arises, where it comes from, and to do that we need to sort of lay out sort of a roadmap of some of the bonding models and models of shape that we have covered so far in general chemistry curriculum. So really we started with sort of the idea of atomic orbitals, and we built that up to a point where we can then understand sort of molecules, right? So in general chemistry you typically start with individual atoms, and again you build into molecules and you continue from there. And so when we get to the idea of molecules, we generally use a couple different models to understand bonding and shape. And so once we understand the electron and its energy, we can then sort of use the Lewis model to sort of rationalize bonding environments or electron domains and how atoms sort of orient themselves and connect themselves to form molecules. So really, again, Lewis is just a 2-electron bond model. Again, it implies or sort of tells us that the electrons are being shared between atoms to make covalent bonds. We can then use that, right, this idea of what types of bonds are existing in a molecule, or what lone pairs are present, again, to count those domains, as they're called. So you end up, again, counting, once you get your Lewis structure, you count the bonds and the lone pairs. And that information can then be used to sort of go on and use what's called valence shell electron pair repulsion theory to sort of predict the shape of the molecule. And so again, in VSCPR, we know that it's just based on repulsions of like-charged things. So we know electrons are negatively charged. So those bonding and lone pair domains repel, and that's going to cause them to orient sort of as far apart as they can geometrically get. So there's only so many shape options that at least we cover in the general chemistry curriculum. But that's what's giving us the shapes of molecules. And it's a pretty useful model in terms of just quickly predicting the shape. Okay, but if we're thinking about it, that sort of leaves a couple topics that we covered in general chemistry out. For example, in these two models, there's no mention of orbitals, which we know are those wave functions that sort of hold electrons. Their probability of finding an electron is defined by those orbitals and their shapes. And we know that it really can't be the atomic orbitals that lead to these shapes, right? So for example, if you had, I don't know, something like methanol, and you drew the Lewis structure out in the Vesper sketch. I'm going to skip the Lewis, but I'm going to draw the Vesper. You would see that you end up with a tetrahedral carbon. Right? You got your oxygen that's actually bent. And let's draw the lone pairs there. Okay? But if we think about the atomic orbitals that are surrounding, for example, let's say this carbon atom, right? We know it can't just be atomic S and P orbitals that are leading to this tetrahedral shape based on the bond angle. So we know that for a perfect tetrahedron it would be about 109.5 degrees. But if you think about, say for example, a p orbital, which is one of the valence orbitals that carbon uses to make bonds, those are 90-degree bond 90-degree angles in those. So if I just draw, say for example, the p sub x and y together, let's call this y, this x. If I draw the shapes of those atomic orbitals for carbon, what I see is something like this. Here's my p sub x, p sub y. That angle there is 90 degrees. So how do you get 109.5 degree angles if you only consider atomic orbital contributions? So we can't do that. So what we need to do is take all of these things and use them, but use an additional model to sort of rationalize everything all together, bonding, shape, etc. So that's what we're going to discuss in today's. All right, so to begin, we need to sort of lay out sort of the basic idea of what valence bond theory is. And so again, it's sort of going to allow us to rationalize covalent bond formation with aspects included that include those orbitals that atoms use to bond, those valence orbitals. Okay, and it's also going to help us sort of combine all of that with, again, shape. So again, in valence bond theory, it's pretty simple. We just assume that, again, these atoms, say for example in, I don't know, let's just use hydrogen to start with. At the simplest example, hydrogen, if I'm thinking about hydrogen atoms combining to form the hydrogen molecule H2, right? You got individual atomic orbitals, so for hydrogen it will be a 1s orbital with 1 electron. Okay, and if I were to draw what that sort of looks like, you got hydrogen atoms with a spherical 1s orbital around them, okay? And if I'm thinking about forming a covalent bond, I'm thinking about sharing of electrons. So valence bond theory says that these two atomic orbitals will sort of overlap, leading to sharing of electrons and a covalent bond formation. Okay, and so that's sort of the basic idea. Electrons are occupying orbitals in the atoms, and that these atoms sort of come in the vicinity of one another and are shared through orbital overlap to make covalent bonds, right? So that's sort of the basic idea of valence bond theory. Now we're going to use some additional examples because, again, as I mentioned earlier, it's not necessarily atomic orbitals in every case that are going to overlap and lead to these shapes that we observe using other theories like VSEP, EPR theory. All right, so let's pick another example. Let's just do, say, methane. And let's think about the atomic contributions and sort of the valence orbitals that are going to bond. And then we can talk about the idea of forming orbitals, or essentially wave functions, probability of finding electrons around these atoms, that will lead to actual covalent bonds and the correct geometries. So again, this is going to sort of lead us into that idea of hybridization. So if I think about carbon, I'll draw it here. If I draw the just the electron configuration of carbon, I have 1s2, 2s2, 2p2. Okay, those are all of the electrons in a carbon atom, but not all of those participate in bonding. We know that the ones that do are called valence orbitals, valence electrons. So those are the outermost. So N equal 2 would be the outermost shell. So that's these 4 electrons. And it makes sense based on some of the things that you've learned in your general chemistry curriculum for looking at the groups on the table and counting up the valence electrons. Carbon has 4 valence electrons. And so they're located in the 2s and 2p orbitals. So if I were to draw sort of an energy level diagram with these orbitals in there, let's say this is my 2s orbital, has 2 electrons. We know that we have 3 degenerate 2p orbitals. Look like this, they're higher energy because a p orbital is higher energy than an s subshell, so on. So here's the 2p, call it x, 2py, 2pz, right? The x, y, and z correspond to Cartesian planes, okay? And so I have 2 electrons there, so I'm going to follow Hund's rule, all that good stuff that you've learned to populate those. Okay, maximizing spin first, and I end up with this. Okay, something like that. Okay, so that's my atomic orbitals of carbon. Okay, and again, if I'm thinking about it, these p orbitals are all 90 degrees from one another. Right? If I draw them on a Cartesian coordinate system, that would be my y. My piece of x would look something like that, and my piece of z would sort of go into and out of the board. I'm going to omit that for clarity. Okay, but that's sort of what I would have in terms of an atomic contribution. Now my hydrogen is just a 1s orbital. Okay, so it's again spherical. I'm not even going to draw that here. It's more, I'm going to focus more on the carbon just so I can show you that. But if I'm thinking about it, none of these are pointed in the right direction to give me the shape of methane, which we know based on VSEPR theory, or at least assume based on VSEPR theory to be tetrahedral. I have roughly a 109.5 degree bond angle, right? Can't be these atomic carbon valence orbitals that lead to that shape. And so what we teach that happens, or what we assume that happens, is that as you sort of take these atoms and you're pushing them together in space to make this bond, make these bonds, these covalent bonds, which lead to this geometry, something has to happen that will allow carbon to make 4 bonds. So electrons have to be in all 4 of these orbitals, and they have to be pointed in the right shape. So it can't be these. And so again, we know electrons, they can be excited. They respond to energy. So the way that what we kind of assume is that one of these 2s electrons, thanks to some energetic factors, gets promoted to a higher energy level. So I'm going to erase this. We're going to think about that. So again, if the hydrogen atoms in space coming close, something energetically happens, and you end up with this. So same axis here, 2s and my 2p's, where one of these s electrons is now excited, and now we have populated all 4 of those orbitals with a single electron. Okay, so things like this can happen that lead to more favorable bonding environments for these electrons. And the whole hybridization idea is that, again, all of these correspond to wave functions, probabilities of finding electrons. So once we get those in the appropriate atomic orbitals, what these orbitals will do is mathematically mix or hybridize, I'm going to abbreviate it like this, to form more energetically favorable combinations of the wave functions, okay? And they'll also have the same energy, right? Because if you think about it, we drew that picture of tetrahedral methane. All 4 of those bonds are the same. The angles are all roughly the same. So it can't be that these atomic orbitals lead to that structure. So through hybridization, through mathematical mixing of those wave functions, we end up with these hybrid orbitals. Okay, so since this is 1 part s, 3 parts p, right, if I mix them to make 4 favorable hybrid orbitals, I will end up with a mixture of all of these. So I'm taking the wave function and mixing them to get 4 orbitals out. However many atomic orbitals you put into this, you'll get out. So, and since it's more p than s, I'm going to have 3 parts p character, 1 part s. I'm going to draw them closer to the p side, but a little bit lower in energy. And we'll call those sp3 hybrids, again, because of that fact. We mix 1s with 3 p's, we get 4 new things out that are going to be equal in energy, and we'll call them sp3 hybrids. And they'll still contain each an electron that can now be used to make a bond or overlap, right? Form a covalent bond with hydrogen's 1s orbital, okay? So that's sort of the idea of hybridization. You're going to use sort of Lewis to count domains, and if I'm counting domains around this carbon, I get 4 domains. That'll sort of give you an idea as to how many orbitals are going to mix to form my hybrids. Okay, so that is hybridization in a nutshell. Okay, and so again, those are all degenerate. Now, when I draw the picture, the valence bond sketch for this, I'm going to show these overlapping orbitals so that we can sort of visually see all of this. And what I want to do is first understand that the shape of an sp3, because the math changed, is a little bit different than just a p orbital and an s orbital. It's sort of a combination of the two. But if I'm going to draw an sp3 hybrid, again, it's going to look a lot like a p orbital, but it's going to really look like that. Okay, that's more of a hybrid orbital, whereas your p orbital kind of look like this. Okay, but you got this one enlarged lobe, one tiny lobe that has some density sticking off the back. Most of the time when we draw these hybrid lobes, we kind of forget about the back end. So this would be sort of how I'm going to draw the picture, kind of like VSCPR for a tetrahedral methane molecule, but showing those sp3 hybrid bonding orbitals. So now let's draw the picture really quick down here below it. I've got my carbon. I know I have 4 hybrid sp3 orbitals that are going to be pointed in the right directions now, equal energy. I'm going to draw them sort of, again, in the right shape if I can. Something like that. Each of those is going to have an electron that can be shared. And in this example, since we're doing methane, right, those are going to be hydrogen 1s orbitals that it's going to overlap. So I'm going to draw spheres. Okay. That also have an electron that can be shared with the carbon atom to make 4 covalent bonds, right, through that overlap in valence bond theory. All right, so let's look at another example, right, because not every time do you get sp3 hybridization. Again, we kind of got to start with the Lewis structure. We count the domains or sites around the central atom, and then we kind of know how many of these atomic orbitals on that atom are going to mathematically mix to make hybrids and an overlap and form covalent bonds with other atoms. Okay, so let's look at HCN. Let's think about a Lewis structure. Again, if you're rusty at Lewis structures, make sure to review that so you know which steps to take to generate a valid Lewis structure. But it's going to look like this. Okay, and so if I'm looking at this central atom, I can count the domains around that atom. Those are either a single bond, a double bond, a triple bond, or a lone pair. Those all four count as a single domain. But I see a single bond and a triple bond, so there's two domains. So that tells me I'm going to mathematically mix roughly two orbitals to get, these hybrid orbitals out pointed in the right directions with the right energy. So let's look at how that happens for the carbon. Again, the bonding orbitals are the valence ones. So for carbon, that's your 2s and your 2p. And carbon has 4 valence electrons. So I'm just going to draw that here. Energy, here's my 2s down here. For carbon, that's going to have 2 electrons, and then my 2p. Degenerate set, my 2p, x, y, and z. The first two are each going to have a single unpaired electron in them. And there we go. There's the valence sort of set of subshells for a carbon atom, our atom of interest in this case, our central atom. Okay, so again, I know I have 2 domains, so that means 2 of these are going to need to mix. But remember, again, I kind of got to think about what will happen to this 2s electron. Okay, that's sort of down here. I need electrons in all 4 of these to rationalize what's going to happen, or I'm going to go through promotion, in other words. But when I bring these other atoms close, some energetic contributor is going to cause one of those 2s electrons to jump up from the 2s into the p orbital there to give me 4 electrons. Okay, and so now I'm ready to sort of consider what's going to happen mathematically, these atomic orbitals, to give me those hybrids that I need. So 2 domains, I'm going to mathematically mix 2 orbitals, and out the other side, once I hybridize, I'm going to end up this time, right, since I'm only mixing 2 of these are actually going to remain unmixed. So I'm not going to touch the energy of those. I'm going to draw my 2p unhybrid, I'll just say y, and 2pz. I didn't really do a good job of making the same energies. Let's try again. There we go. No energy change. They're unhybridized leftovers. Now again, I put 2 orbitals in to mix. I'm going to get 2 out. So now, since it's about 50-50 s and p, I can draw them about the same distance in between the 2, roughly. That's not a very good job, but you get the idea. If I have my energy scale on one side, these would be sort of in between these 2. Okay, so there's my p, 2p y, 2pz, still unhybridized. And then now I've got these 2 hybrids, now with appropriate energy, and hopefully pointed in the right direction to make the geometry we're observing. And so what we call those, since we only mixed an s with a p, we call those sp hybrids. I mathematically mixed an s and a p, I get an sp hybrid, just like we took an s with 3 p's and made sp3 hybrids. But again, orbitals in equals orbitals out. If they're unhybridized, draw them appropriately. Okay, don't mess with those. So these are going to be my 2 sp hybrids. Okay, each of those containing an electron. There's still electrons in the other 2. Okay, so now if I'm thinking about HCN, I can now draw my sketch of what this looks like and show those orbital overlaps that form these bonds. Okay, so I'm going to start with the central atom, and I know that just like BSAPR theory, when I have 2 domains, they're 180 degrees apart. So I'm going to draw my sp hybrids 180 degrees apart, maybe a little fatter than just the p orbital there, and each of those is going to contain an electron. Okay, I know that hydrogen's only got a 1s orbital that's not going to need to mathematically mix or do anything, that's going to overlap with one of these carbons providing an electron. So there we go, that end of the molecule is taken care of. Now for my nitrogen, I kind of have to sort of assess the same thing. I got to think about the hybridization of that nitrogen. And fortunately, I can take what I've done here for carbon, so this will be for carbon, and I can sort of do the same thing for nitrogen. Then maybe we can think about what's left and how that's going to line up with what we've sketched so far. So let me quickly sort of modify this for the nitrogen atom. And we'll just kind of start from scratch there. Let's just do it that way. So for nitrogen, you just have one more valence electron, so you end up with this. So now this is for nitrogen. There's the atomic orbitals. Okay, got one additional electron in the valence of nitrogen. Again, no need for promotion. We have electrons in all four orbitals. Okay, so all we need to do is think about mixing. So if we count the domains on our nitrogen atom now, I see I have a lone pair here and a triple bond. That's two domains. So I'm going to end up mathematically mixing two of these, okay, orbitals, really, to get my sp hybrids, and I'm still going to have two unpaired electrons, two orbitals that are not mixed that I gotta keep where they're at. So now let's hybridize those. And what I get my 2p, y, and z remaining unchanged in terms of energy, each with an electron, okay? And I'm going to get sp hybrids, okay? So here, again, 50% p and s, so I'm going to try to go between them. I'm not going to do a very good job. But I know two of those electrons from what was the 2s are going to be there, and I know a single electron is going to be there in those new sp hybrids on the nitrogen, okay? So now if we think about that, we had sp hybridization on our carbon, and we're going to have sp hybridization on our nitrogen. So naturally, one of these hybrids on the nitrogen is going to overlap along the internuclear axis with the sp of the carbon to make a sigma bond. Okay, and of course I still have one sp hybrid that's going to contain a pair, and that makes sense based on our structure. That's actually the lone pair that you're going to see on that nitrogen. But I still have some other things that I haven't worked into this structure, and so we're going to have to think about that a little bit. So on both carbon and nitrogen, we had two unhybridized p orbitals, each with one electron unpaired. So the way that we depict that in valence bond theory, when we draw these hybridized structures, is we leave those p orbitals as sort of almost like Cartesian axes. So here I have, it's a YZ as I've labeled, but I'm going to have sort of an orthogonal p orbital that's again orthogonal to those 180 degree apart sp hybrids. But I'm also going to have orthogonal to that another unhybridized p that will depict like this. Okay, so again, p orbitals are 90 degrees from one another in terms of Cartesian coordinates. So I'm going to depict that in my structure. Now naturally, again, both the carbon and the nitrogen have that left over, so I'm going to draw them for each of those atoms. So here is one of my p's for nitrogen. Here's going to be the other, 90 degrees apart in 3 dimensions, if you can imagine that. So it's going to look something like that. Now again, the way I've depicted it, here it's got a triple bond. So we've got to think about what that really means. So a triple bond always contains one direct, along the internuclear axis overlap of orbitals, and then it's going to contain two above and below sort of sets of overlap, above and below and left and right. So the way that we draw that, or make these what are called pi bonds, is we're going to connect those p orbitals that are each going to have those electrons, right? They have to be aligned to sort of overlap. You can't connect, say for example, this one with that, this up and down or vertical p orbital on nitrogen with sort of the orthogonal one on the carbon. So we're making sure they connect appropriately. But again, each of those is going to contain those other electrons that are going to do the pi bonds, right, for that cyanide, hydrogen cyanide, okay? So again, just to sort of recap, each triple bond is going to contain two of these pi bonds and a sigma bond. If we had a double bond, it would contain one sigma and one pi bond. So we'll probably do an example of an sp2 hybrid next, just so we can think about that. But again, what the valence bond sketch and the hybridization tells us is that, again, it gives us sort of what orbitals are overlapping to form these bonds, as well as the shape. For an sp hybridized atom, you have a very linear shape. Okay, for a sp3 hybridized, as we saw, tetrahedral shape. Okay, so all that sort of correlates really well with what we learned using VSEPR theory in the past. All right, so let's continue with our discussion of hybridization, the valence bond theory, as a useful predictor of orbital overlap and covalent bonding and shape. So we're going to use this particular example. This is formaldehyde. I've already got sort of pretty much the VSEPR sketch up here for us to count domains and sort of go through the process of hybridization to draw a good valence bond sketch and look at things like shape and orbital overlap. So just to recap, we learned about two different styles of orbital overlap sort of in the last video. I threw them at you, but I just want to recap that here. So sigma style overlap is direct along the internuclear axis. Okay, those are sigma style bonds, sigma style overlaps, what I call it. Okay, so every bond in the Lewis structure, a single bond, each bond has a sigma style set of overlapping orbitals, right, to make those covalent bonds. Then we learned about pi bonding or pi overlap. This is above and below, or left and right of that internuclear axis. So the way I like to think about the internuclear axis is it's sort of like, you can pretend like they're apples, these atoms are apples, and you have an arrow that's going between and getting both. That arrow would be the internuclear axis, okay? So that's the styles of overlap that we're concerned with here. So let's round out our discussion of hybridization, VB theory, as it might pertain to organic chemistry with an sp2 hybridization example, okay? And we'll label our final valence bond sketch with all the orbitals that are overlapping with our sigma and our pi bonds, all that good stuff, so you get some practice doing that. Let's use a simple example like formaldehyde. Okay, seen here we can count domains on our central atoms. We can look at all the atoms and think about what orbitals are there, atomic, otherwise. But for this carbon, there are going to be 1, 2, 3 domains. I've got 2 single bonds and a double bond of electron density. For that oxygen, I'm also going to have 3 domains, right? I got a double bond, 2 lone pairs. And we, of course, have hydrogen, so there's just going to be 1s orbitals, right? So again, if I'm thinking about this, I have 3 domains, so those are the same, so the hybridization is going to be sort of similar. Okay, but I'm going to go through the carbon. I'm going to show you where the hybrids come from again. So again, we're practicing this heavily so you understand where all this comes from and what these sketches mean. And then I'll do it for the oxygen to sort of show you the difference, sort of point out when something might be pretty easily observed, such as a lone pair, right? It's pretty easy to tell when you've done well with your valence bond sketches from a Lewis structure if you have lone pairs on the right atom. So let's sort of go through those steps again. All right, for carbon again, as in the past, there's my energy. Got a 2s atomic orbital. I got 3 degenerate 2p's. Okay, my s has 2. My p's have 2 unpaired, 1 and 2 of the atomic orbitals there. Of course, I got to go through promotion here, I'm going to go through promotion here, and one of these is going to be excited to put electrons in all the orbitals that we're going to need. So here, if we redraw this atomic orbital of carbon, something like this. Now promoted, I got 4 electrons in the orbitals. 2p, 2s. And again, if I'm thinking about the domains and counting the domains, I got 3, so I'm going to mathematically mix, right, when I go to form this molecule, 3 atomic orbitals to generate 3 degenerate hybrids. So this is my hybridization step, mixing the wave functions. So again, I'm going to have one unhybridized thing that I'm just going to sort of draw kind of where it was, and now I'm going to have an S mixing with 2 P's to get 3 hybrids out. I put 3 orbitals in, I get 3 out. And they're going to be 2 parts P character, 1 part S. So I'm going to draw them a little closer to the P there. I'm running out of room, so I'll make it a little smaller, but there we go. Okay. It's not very much to scale, but you get the idea. I should draw them a little closer to where the P orbital is. Let's just do that. There we go. So there's my sp2 hybrids because I mixed an S with 2 P's. Each of these will be an sp2 hybrid orbital with the right energy, equal energy, pointed in the right directions. And I still would have, let's call this a 2p sub z unhybridized orbital. Making sure I put my electrons back in there in the drawing. So I end up with something like that. Okay. So if I'm starting to draw my sketch, I can do so. We'll start with that central carbon atom. I'm going to draw 3 hybrid equal energy orbitals. This is kind of like Vesper. They're going to be equidistant from one another in terms of geometry. Okay. So here, I'm going to draw it kind of like this. I mean, you can draw these kind of any way you like, but I'm going to draw mine kind of like this. So there's my sp2 hybrids. Okay, pointed in the right directions. Again, pretty much flat. Sort of trigonal planar geometry is what it looks like there. Okay. I know that 2 of those are going to have hydrogen atoms bound to them with that 1s orbital overlapping to share an electron to make a sigma bond. Each of those is a sigma bond, so I'll just draw the sigma to denote that. And now I got to kind of think about this oxygen, its hybridization, how it might overlap with the hybrid orbitals of this carbon. And again, if I remember, just like a triple bond, a double bond is going to contain not only a sigma style or direct overlap, but it's going to contain 1 pi bond, which will be above or below, left and right. So I've got to kind of think about all those things to put together a good sketch. So for oxygen, same idea, different numbers of valence electrons. Still have 2s and 2p atomic valence subshells. So for oxygen, you're going to have full 2s, and you're going to have 6 valence, right? So one of those 2p's is going to end up having a pair in it. So if I think about it, everything's occupied by electrons. No need to worry about the promotion step as much here. So if we think about it, if I count domains again, 3 domains, I'm going to mathematically mix 3 of these atomic contributors to get, again, new wave functions pointing in the right directions with equal energy. So that's going to be my sp2 hybrid. So let's do that. So hybridize. I got 1 unhybridized p. Try to draw up the same energy. My 2p, let's call it z, whatever. And now I'm going to have 3 sp2 hybrids, a little bit closer in energy to the p if you can. And so 2 of those are going to contain paired sets. 1 of them will contain an unpaired electron. Okay? And if I think about it, that makes a lot of sense. When I go to draw this, the sp2 hybrid with a single unpaired is going to be favorable for sharing to make a covalent bond or a sigma style bond with that carbon. The other 2 sp2 hybrids that I'm going to draw, again, basically 120 degrees apart from each other if I can, are going to contain the lone pairs that I see in the Lewis structure or the Vesper sketch here for formaldehyde. And if I think about it, I didn't show it yet on the carbon, but I know that there's an unhybridized P that contains an electron in both the oxygen and the carbon that I'm going to need to make sure that I draw so that they can form that above and below or left and right overlap of my pi bonds. Let's just pretend there's an electron from each to make that pi bond between the 2. So that would be sort of a valid structure for formaldehyde. Now what I didn't do a good job of showing is that these sort of ears containing the lone pairs are going to sort of be pointing into and out of the board the way I have it drawn, but depending on how you like to draw them, that's easier to show, right? So I can try to draw one bigger than the other to show that one's coming out of the board at you, one's going in. I'm not very good at doing that, but does that make sense? These are sort of going to be orthogonal, like something like this, right? Maybe let's draw an oxygen to make it easier to see. So there'll be a lone pair in this lobe that's going back behind the board, a lone pair in this one coming out of the board. Didn't do a good job of depicting that here, but I think that that does a pretty good job. And again, we can kind of see all the orbitals that are overlapping, both in a sigma style fashion and a pi style fashion. We can see the lone pairs, we can think about shapes. And so again, what we see is that for sp2 hybridized things, without even having to draw the picture beneath the organic, you're going to know that this is a very flat molecule with, again, these unhybridized p orbitals coming out above and below that contain electrons to do the pi bonding. Okay, just like in your sp hybrid, you had the the unhybridized P's that were orthogonal that did your triple bonding, and you had a very linear shape. That'll sort of be really important to note when you go to look at organic molecules. And importantly, you're going to know, again, what orbitals those electrons were occupying when they formed those bonds. Okay. So thanks for watching. Comment, leave some input below if you like, didn't like things, so that we can develop some other interesting videos for you. Thanks. See you later.